We'll continue now our study of set theory with some useful rules for set algebra. We've already seen something similar to the first part here in our studies of logic. These are sometimes called De Morgan's laws. And they say that in the first case, the union of two events has complement equal to take the complement of the first event and then intersect it with the complement of the second event. Similarly, if I want to know about the complement of an intersection, it's enough to take the complement of the first and union it with the complement of the second. This point here is somewhat interesting philosophically, which means it just says that nothing is in the set A and not in the set A. So I think it certainly squares well with our intuitive notions of logic. Either a point is in the set A or it's not in the set A. So the only thing in their intersection is the empty set. Some other kind of obvious remarks when you think about them are, if a set B is contained in A, then unioning A and B does not change A at all, because I haven't introduced anything that wasn't already in A. Hence, the union of A and B is just A. And I'll say this is because nothing new has been introduced to A, because everything in B is in A. Similarly, when I take A and I intersect with B, I just get B. Like this. Because everything in B is already contained in A. So I get all of B back from the intersection. Usually when you take an intersection of sets, you end up with something that's not equal to A and not equal to B. That you get something smaller than both of them. Think back to the Venn diagram. But in the case of a subset, you actually get that the intersection is exactly equal to the smaller one. A few more nice laws here. A union B intersect C equal to A intersect C union B intersect C. And A intersect B union C is equal to the intersection of A union C and B union C. So essentially this is saying like how to distribute intersection and union. So let's look at a very concrete example and test some of these different properties. I'll take the first set A to be the set of all real numbers that are greater than or equal to 3. In interval notation, if you're familiar with this, this is 3 to infinity, where I include the endpoint, 3. The second set is the set of all points that are less than or equal to 5. In interval notation, minus infinity to 5, and then this should be a square bracket, because I include 5. So let's look at the different values I get, or different sets that I acquire, from unioning and intersecting these sets and then also things related to their complements. So A union B is all points that are either greater than or equal to 3 or less than or equal to 5. And this is easily seen to be all real numbers. Every point is either greater than 3 or less than 5. Conversely, the intersection will be all points that are greater than 3, but also less than or equal to 5. So what are these points? These are the points 3 up until 5, and where I can include both of them. Not A union B. So this means either not in the interval 3 to infinity, or in the interval minus infinity to 5. What does it mean to not be in this interval? This means I'm in the interval minus infinity to 3, because I am less than 3. So what is the union of these things? Well, it's just equal to minus infinity to 5 inclusive. Similarly, in the second example on this slide, I'm either in the interval 3 to infinity or not in the interval minus infinity to 5. But what does it mean to not be in the interval minus infinity to 5? It means I am in the interval 5 to infinity. So this whole union is just equal to 3 comma infinity. So now we're getting tricky. Not A or not B. So let's write it out. Not A, we've already established, is the interval minus infinity to 3. It's everything that is less than 3. And not B is equal to, close, 5 to infinity, where I don't include the endpoints. So what is this union? Well, it means I can either be less than 3 or greater than 5. So this is equal to everything less than 3 or greater than 5. And the typical way to write it is actually as a union of intervals. Minus infinity to 3, union 5 to infinity. So in this case, it's quite common when you have two disjoint intervals that together make up your set to combine them just via this union notation. So now we'll switch and talk not about unions of these sets, but intersections. So we'll look for the points that are in common to both. So again, we'll write this out. Intersect A, or complement of A is equal to the complement of 3 infinity. So what is not in here is minus infinity up to 3. And then B, of course, is still minus infinity to 5. So what is included in both of these? Everything from minus infinity up to 3. I had to take the smaller right endpoint because I need to be in both of these sets. So let's play a similar game. Recall that A is equal to 3 to infinity. And the complement of B is equal to 5 to infinity. So what is in both of them? It is everything from 5 to infinity. Now I take the larger endpoint here because, again, I have to be in common to both of them. The point 4, for example, is in the first interval, but not in the second one. Therefore, it's not in the intersection. So as a last example, not A is the set minus infinity up to 3, and not B is the set 5 to infinity. So what would it mean to be in the intersection of these two sets? Well, it would mean I would need to be between negative infinity and 3 and between 5 and infinity. Said another way, the only thing that could be in the intersection of these two sets are numbers that are less than 3 and greater than 5. There is no such number. Nothing can be less than 3 and greater than 5. Therefore, there is no intersection here. Or, to use the language we've already developed, the intersection is equal to the empty set. So the intersection of the complement of A and the complement of B is the empty set. Because no numbers are less than 3 and greater than 5. So we'll conclude our study of set theory with one more notion that could appear on the CLEP exam, which is the notion of Cartesian product. What is a Cartesian product? It says take two sets and create a new set out of them. Now the elements of my new set will be pairs of points. The first point will belong in the first set I producted, and the second pair, or the second coordinate, will belong to the second set. So let's look at the mathematical notation. We say A cross B, or the Cartesian product, is the set of points A, B, so pairs, such that A is in the first set, or little a, and little b is in the second set. So in other words, a Cartesian product of two sets is a set of pairs of elements with a specific ordering. The first coordinate comes from the first set, second coordinate comes from the second set. And I'll make a remark that unlike the normal notion of product, which is commutative, so normally multiplication is commutative, i.e. A times B is equal to B times A. That is not true for Cartesian products. The order is very important, and we'll see that in the next example. So here are two simple sets that each just have three elements. We have the first set is 1, 4, 5, and the second set is 2, 4, 7. So let's examine several statements and decide if they're true or false. So the first one is just a quick review. The statement is A intersect B is empty. Another way of saying this is nothing in A is contained in B. Is that true? No, it's not. The number 4 is common to both of them. A intersect B is not empty. It contains the number 4. Let's move on to the first question about Cartesian products. The statement is the pair 1, 1 is in the Cartesian product. Is it true? Well, 1 is contained in the set A, but 1 is not contained in B. Which violates the definition of the Cartesian product. So this is false. Let's look now at the pair 4, 4. Is that contained in the Cartesian product? Well, let's look and check. Is 4 contained in A? Yes. Is it contained in B? Yes. So this is true. Because 4 is contained in A and 4 is contained in B. Great. Next one. 1, 7 contained in A cross B is the question. Is it true? Is 1 contained in A and 7 contained in B? Yes. We see 1 is in A, 7 is in B. So 1 is contained in A, 7 is contained in B. Very good. So is 7, 1 contained in the Cartesian product? This is related to the question of, is the product commutative? Is A times B the same as B times A for this kind of product? Well, we have to check. Is 7 contained in A and is 1 contained in B? 7 is not contained in A, so we know it's not in the Cartesian product. And 1 is also not contained in B. So very strongly, this is not contained in the Cartesian product. This is false. Because 7 is not contained in A, and 1 is not contained in B. Last question is just making it slightly more complicated by introducing the notion of intersection to Cartesian product. Is 4 comma 7 contained in A intersect B cross B? So this is, I think, harder, so let's check. Is 4 contained in A intersect B is what we have to check. It is. It is in both A and B. So we'll say yes. And is 7 contained in B? The answer is yes. So 4 comma 7 is contained in A intersect B cross B. So the statement is true. So we've looked at more delicate notions of how to intersect sets and union them with respect to complements. We've also introduced a notion of Cartesian product. This is just the beginning of set theory. It goes in many beautiful mathematical directions. And if you're interested in these things, I encourage you to explore a little bit on the internet. It's quite a wide world with lots of connections to other interesting aspects of human knowledge.